In our previous implementation, we looked at how to generate images using a two-dimensional grid with Python and pygame. And now you can see that after playing a little bit with the program, I have generated a decent collection of images that now we need to rescale for a final resolution of 28 by 28. Because even though each of the tiles pixelate one square of dimensions 16 by 16, the total width and height of this canvas is not the desired resolution, and therefore by passing it through a neural network it will make the program rather slow, and it doesn't really provide any additional information, so we need to make the images smaller. To do this, we're gonna make a mirror folder called res images, and you can see that it contains the exact same subfolders as the original images path. Of course, you can make this using a form of procedural programming. You can also you can use a special library known as OS that focuses on the operative system, and then there is a method called oswalk that allows you to go recursively through every single subfolder, and you could do it that way. However, I thought that that would make the tutorial a little bit more complex and could potentially deviate from the main objective here. So what I'm gonna do now is to generate a new file. And that file is gonna be sitting here next to main.py. It's gonna be called utils.py. I could call it rescale because that's generally speaking what it's gonna do, but sometimes I like to add some additional helper functions to it, so I don't know ahead of time the scalability of this project. I'm just gonna leave it as utils. So the program is going to be divided in 3 sections as it normally does, and these are going to be the modules, the definitions of data in the code. So let's talk a bit about the general process. We have a series of folders, and each of those subfolders has a set of images. So we need to take every single one of these images and rescale them to a final resolution of 28 by 28. This will be accomplished by using the Python library CV2, which stands for OpenCV. The OpenCV library is a very powerful tool that was developed not only for Python, but is also available for compiled programming languages, and there is also extensions for Unity so that you can use it. OpenCV allows you to traverse matrices of data. Because images are a representation of this dimensional array system, it's possible to go through all of the elements quite quickly. OpenCV feeds on a library known as NumPy in order to extract and facilitate operations between matrices. So we're going to import CV2 because one of the methods of this library allows us to resize images. We're going to import the random library just in case. We may erase it if we don't need it. And then we are going to import the OS library. The OS library allows us to access our computers directly from Python. And it has good support for most operative systems. We are also going to use a special method from inside of the OS library. However, it is also inside of the path sub library, and therefore it may be useful to import it from that sub library. So we're going to say from the OS path from the OS library, path sub library, import the join method, and we're going to give it an alias. We're going to call it JN. That is something that you find quite often on the internet. This is kind of like a convention for that particular line of code. So before we move into the data definitions and the code, let's just practice a little bit with the OS path and the join library so that you can see what it does. So let's try to traverse the folders. To do that, we need to specify first in the data definitions a main path. And this path will be represented by the dot. The period represents the location where I'm currently running the utils.py file, followed by the / so that I can enter the sublibrary images. That is going to be the main path of reference. We're also going to need a destination path, and that destination path will be the mirror folder system, but this time referring to the resized images. Let's see how we can access the images from within the images folder. Because they are not immediately accessible, they're inside of their own subfolders. we need to use a method known as list.dir, list directories. So we're gonna traverse through all of the different files and subfolders using a for loop that is gonna go through every folder in this path. However, this path right now is just a string. To tell Python that we want to use this as a location in our computer, we use the OS library and then we apply list.dir. For each of those folders, we're gonna print the name of that folder. If I run this program right now, you'll notice that we have printed out a list of the different folders that are located directly inside of images. I can go a little further and I could instead create a target folder, which is gonna be the target sublibrary, angry, happy, and sad, with reference to the location, the absolute path inside of my system. That is to say, I need to join using the join method, the original path with the name of this folder. And if I print the target folder and I run the program once more, you will notice that this time we have the, well, in this case is the relative path, because it's giving us the context of where we are relative to utils.py. I guess I misspoke when I said the absolute path. And now let's see if we can iterate over every single one of those subfolders. We can say for every file or image, we could call it image. Let's call it a file. In the list of directories of the target folder, we can print each of these files. And if everything works well, we should have printed out every single file that is located inside of these subfolders. There is a way, of course, to discriminate whether or not these are PNG files, but in our case, there is no way to add additional files that are not images. So we're just gonna leave it like this. The utility of this syntax is that inside of this second for loop, we still have access to the folder. And to demonstrate that, I'm gonna print the relative path. I'm gonna call it the relative path file, and this is gonna be a joint version of the target folder with the particular file of interest. If we print it out, we should have now a more comprehensive address where we can find these images. The reason why this is useful is because here we can implement the algorithm. We can resize the image, we can rename the image, and then we can save the image. To resize the image, we need to know what are going to be the final dimensions that we want to rescale into. We will start by reading the image by typing im read, and we're going to pass as first argument the relative path file, followed by a very special command called cv2.imreadUnchanged. That will make sure that we read the image as is without making any transformations into it. So after reading it, we need to save it. We're going to call this the img for image, and now we can resize it. We can set a rescale version of the image, and this is going to be equal to cv2.resize. And inside of resize, we're going to add the original image followed by the new dimensions of that image. And I'm going to give it as a tuple of 28 by 28, which is the final desired resolution. So let me just print the shape of one of these images, and let's see if we get any errors. Okay, no errors, that's fantastic. So the image have been properly reshaped. And if you're curious about this attribute, so the shape attribute tells us as a tuple what are the number of rows, the number of columns, and the number of channels inside of each of the images that we are working with. So this is a three-dimensional lattice. So now that we have this, it's just a matter of exporting the file. And to export it, we can say cv2.imwrite, and the first argument will be the destination and the new name. So I guess that we should follow the comments here and rename the image. So the next step will be to rename the image, and to do that we are going to create a formatted string version attached to the new relative path. So we're going to call it new image name, and this should be equal to a joint version of the destination path, which is the new location called res images, and that is represented in our program with the constant parameter, the string parameter dest path. Then we specify the relative target folders, which is the relative path, which hasn't changed. However, it may be a good idea to rename the files as well. We are going to pass the name of the folder. We're going to pass the name of the folder, which hasn't changed within the sub libraries, and then the file name. And here I can specify any modifications to it. So I'm going to add the number representing the resolution of this image. I'm going to start with a formatted string version of it, and let's call this a new file name. This variable will be created in a previous line. I don't make it in this line because all of this is gonna enter its own formatted string, and therefore I need to put this within the curly brackets and press F, and we're gonna finish with .png. Here we're gonna set new file name is gonna be equal to the original file name, and at the beginning I'm gonna add the number 28 followed by an underscore, and then we add the name of the file. I don't add it afterwards because the last element in file is the extension .png, so I don't want it to say .png 28. So now that we have this, let's just print before we save the image. So let's print the new image name and let's see what we get. Okay, so we have some relative directories with the name of that new image. So let's check if this path exists. And there is multiple ways to do that. I guess that something I can do is to just copy it and see if this path exists. Oh, look, there is a duplication on the name.png. So it seems that this doesn't even need to be in formatted strings anymore. It just needs to join. So let me run it again. And that should do it. Okay, so these paths don't really exist yet because I haven't saved them. So I need to try to save the image in the new image name in the new directory with that particular image name. I guess that this is not required here either. So it would be just the destination path and the folder, and then we write the image. Let's see if this works. The problem is in line 21. Okay, and after that, I need to pass the actual image, which was the rescale image that we created in line 16. If I run it once more, this time we didn't get any errors. So let me see if the images are in their subfolders now. So we have the res images, we have the ngRes sublibrary, and yes, we have a modified rescale version of each of the images that we created for that particular subfolder. Let's open it with Paint, this very sophisticated program that has existed forever in Windows platforms. And let's click on resize just to check the values in pixels, and it is 28 by 28. Perfect. Hopefully the algorithm that we generated will be a nice addition to your toolkit so that you can create specific implementations of neural networks using datasets similar to the MNIST.